Yeah, as I was saying, this is my second time presenting. And if I could, I'll just give a little plug just for the conference and encourage people to present, even if you're kind of shy like me. You don't like presenting. It's an awesome opportunity. The last time I presented, it was 8 years ago. It was generating data using Prolog. And to this day, I still get responses from people out of the blue. And it's quite gratifying to get that. It's maybe the same will happen with this presentation. For me, what really drives it is I have a message I want to get out that I think is important. So that's why I'm here today. And that's why I was here 8 years ago. So here I am again 8 years later. So not only am I making a plug to present at the conference, I'm talking about what it's like to present at a conference. So in a sense, that's a meta concept. And so a meta conference would be a conference where you're talking about conferences, for example. So I'll get into that a little bit later. And so I'm going to talk about what meta is, metadata. I'm going to talk about scalability. And before all of that, I'm going to talk about test automation because that's why we're here. And there's a basic assertion that I think I want to make sure we all agree on. Let's see. Test automation. Okay, so hopefully we can all agree that agile projects require continuous integration. Continuous integration is not possible without test automation. So you've got to have good test automation, you have continuous integration. And without that, you have bad agile. So, so what does bad test automation look like? It looks like tests that are very expensive to maintain, to develop, tests that might give too many false fails that you have to look at and try to figure out what's going on. And that can slow down the CI pipeline. And most importantly, tests that take too long to run. So those are the things in particular that can really slow things down. And in Agile, you cannot have that because you're trying to pump stuff out every week or every 2 weeks on a cadence. And if you hinder that, you're going to really slow things down. And then ultimately the customer's not going to see stuff when they should be seeing it, and that they're going to get upset. So scale. Okay, so we'll talk a little bit about scale. Scale can mean size. So questions like how big something is, how long will it take, how much will it cost, how many lines of code, how many users, bandwidth, other capacity questions. So that's pretty obvious, but what's less obvious is scale also can mean proportion. So when I was a kid, I built models. And so on the front cover of every model, like a boat, a car, an airplane, it would mention the scale, and it's expressed as 1/87, 1/64, etc. That's important because it gives context, and it's not just saying that something's big or small, it's saying it's this big relative to something else. So it's really important when you're talking about size and scale in particular to mention a number because it makes it more meaningful. So if you can't scale something, or if you can't express scale, it's going to be hard it's going to hinder your scalability, your ability to scale, to grow something bigger. And I'll talk a little bit about that later. That's not an accident, that's Chinese character. My excuse for having that is my wife is Chinese, but I like that because in Chinese, scale is really two words put together. It's compare to an example. And in Chinese, that's pronounced bi li. So I like that because it's just a reminder that scale's always in relation to something, and that it has meaning in that sense. So sometimes I think the tendency is just to forget about that and just say, oh, we're going to make something that's scalable. But it's not that meaningful unless you can put a number on it. Scalable equals expandable. So if we're talking about growing a system over time, you can scale something up or you can scale it down. So today we're just going to be talking about scaling up because that's what the problem most confronted with. But scaling down, I'll just talk about it for just a second. An example of that might be downsizing a company. It might be phasing out an operating system. And there's certain steps that you would do to do that. Today, we're not going to talk about scaling down. We're going to be talking about scaling up because that's the problem we're most confronted with in software design. So what might that mean? Increasing the capacity of a system by X times. So we're putting a number on. Increasing the number of users by X. Increasing the bandwidth by X. Increasing the number of cooperating entities. X entities instead of a non-quantified number. So challenges to determining scale. Biases. So these may be unconscious ones. Your state of mind, your emotional state of mind. So when you may be depressed or you might be super excited. So it's going to color your ability to make a judgment on size or scale. Lack of experience. So this is another one where you'll get somebody that doesn't have a lot of experience and they may not be able to give a knowledgeable assessment of what the size, that's appropriate size would be. Other things that can get in the way are politics, internal or external. I'll give you an example of that a little bit later. Other blind spots, whatever they might be, conflicting priorities. So these are some of the things that can get in the way, and I'll give some examples in a minute that are kind of fun, and to really drill down on this. Scale, sizing a project. So I don't know if anybody recognizes this book, but it was written in 1975. And you can tell by the title that it's quite dated. And so I don't know if this was a time when only men worked in software projects or not, but clearly that's not the case. But anyways, the mythical man month. His whole point here is that he's trying to, you can't size a project based on this notion of a man month. So a man month would be how many months it takes for a single man to do something. So 10 man months would take a single man 10 months to do something. But his point is you can't have 10 men doing that in 1 month. It's not, the relationship between men and month is not linear. So he also gets into, so by the way, so this whole notion of, this book was very popular up until the .com book, but the .com period, like around 2000. Around the same time, extreme programming came into vogue, and then it eventually developed into Agile. But it borrowed from some of these concepts. And one of the important concepts from this book that was since evolved is that it's really hard to size a project way off in the future. It's much easier to size stuff that's right in front of us, like a story. How many points is this story? And the reason for that is there's fewer variables involved. We can see kind of what's right in front of us. Stuff does not change as much. Whereas you're looking a year down the road, 2 years down the road, you can't see that far, right? And so Agile is really just built around that idea where don't worry about those long-term goals. Don't worry about the long-term size. Look at what's right in front of you and focus on that. Because it's easier to size. So let's talk about sizing a project. So this is probably the most famous. This is not just a project, it's a program. Because it's actually many projects, but for the sake of discussion, we'll just think of it as a single project. This is maybe the most famous project in our lifetime. The Apollo project, the mission to get a man on the moon. So what's astounding about this is that JFK came up and announced in the early 60s, he said, we're going to get a man on the moon. And sure enough, we did it. So that to me that's kind of, you never see this in government-run projects, but this is a case where we actually have seen it. But look at it, it's way over budget. So it was planned for 7 billion, sorry. Back then, the dollars were a little bit different. And the actual cost was $25. Now you got to take this with a grain of salt because I got it from ChatGPT, but ChatGPT is probably in the ballpark. Okay, so we'll go through a few examples that are not necessarily project based, but they're really basic, and it just goes to it will illustrate to us how difficult it is to size something. And if it's difficult to size a frog, for example, it's going to be much more difficult to size a project, right? So I'm going to give a little story here about sizing a frog. So maybe about 20 years ago, when I was really into backpacking, I was out with my buddy. We had hiked up all day, pretty high up in the altitude, up into the high Sierras. We're sitting around after dinner, around a campfire. It's real quiet. We're drinking scotch, chilling, looking at the sky. And all of a sudden we hear this frog. And it's loud. It's like my friend's here, and it sounds like a loud belch. So it feels like, wow, this must be a big frog. In fact, I'm thinking toad. I'm thinking that it's about this size, right? So my buddy says, okay, let's go out and find this thing. So we go out with our flashlights, and it's cribbiting maybe every 30 seconds or so. And so finally, after about 10 minutes of searching, we find this thing. And it's not this big. And it's not this big. It's this big. It's this big. So I missed it. I missed it by about 2 orders of magnitude. So that's an example of just in very simple example where we can miss things. Like we can be way off, right? And so I've kind of come back and thought about that. Why was that? Why did I miss it? And so part of it is probably a lack of experience. So I'm not a frog biologist. That's part of it. Another one might be my state of mind. You know, I've been drinking scotch. I'm way up in the altitude. That can affect how you think, right? The acoustics. There was some granite around this little pond where the frog was. And it's also very quiet. And so maybe even the smallest sound would sound big. So these are some of the things that can color your perception of physical reality or virtual reality for that matter, and not necessarily give you an accurate picture. Here's another example that really continues on this point of really trying to figure out how big something is. So this example is about, I got this from a book by Wendy Williams about butterflies. And so it's it's a very well-written book. Even if you don't like butterflies or you're not into it, it's a really good read. The title is, let's see if I have it here. Here it is. I love this book. Language of Butterflies. This is a morpho butterfly here. And so I'm 2 chapters into this, and she asserts that there are X number of species of butterflies. And so I went, what? Are you kidding me? So I'm going to put this question to you guys. how many species of butterflies do you think there are? We can say 1,000, maybe 10,000, 100,000, million. Yes, 10,000. Anybody else?
Million.
1 trillion.
What?
1 trillion. Yes. So that was exactly my reaction. What? So it turns out we've only discovered 1 million so far. So now it kind of begs the question, do we 1 trillion? Maybe the person that came and stated that is way off base, you know. But I'm assuming that that's fairly correct because scientists have looked at this for quite a while. So if somebody told me that there were 1 trillion butterflies in the world, I would say, yeah, I could go with that number. But 1 trillion species of butterflies, which means in reality, the number of actual butterflies is trillions and trillions, right? So there's something about size that it's we struggle with, and I think part of it is we struggle with large numbers. So let's talk about scalability now. If scale is relative size, scalability is relative expandability. So I mentioned this a little bit earlier, but if you can't determine the size or scale of something, then you're probably going to struggle with scaling. And this is important because usually you need a number to inform your design decisions. So for instance, if you're going to scale it 2 times, maybe you don't design for scalability because you don't need to. It's not worth the effort. Maybe if we're going to scale it an order of magnitude 10 times, maybe we choose one path for designing it versus whether it's 2 orders of magnitude. Maybe we make an entirely different decision. Now that said, sometimes we won't know. We won't know what that number is. And so that's part of what Agile is, right? We may not know, but once we do know, we should start taking action. Otherwise, what's going to happen is you're going to start collecting tech debt and you might drown. So that's what kind of, in my example a little bit later, you'll see that. I'll demonstrate that. Sizing a universe. So imagine, for example, that these are test cases. Okay, so this is kind of what I'm in QA because I like this problem more than I do necessarily designing something or a product. I like testing a product. And for me, what you have is combinations upon combinations upon combinations of things that need to be tested. So a lot of times with junior engineers or QA folk, what they'll do is they'll look out at this universe and just pick off 1, 2, 3, one at a time. And that's not going to get you there because you've got billions of stars out there, right? Now, this is on 2 dimensionals, but in reality, it's multi-dimensional, right? So there's a 3rd dimension, which is the depth. There's a 4th dimension, which is time. So let's talk about the 4th dimension, time. Those are stars that the light has not yet reached us. It's out there, but we don't see it yet. Why is it? Because this hasn't come. So this might be a change that comes later in time. So if we can anticipate what that change is, great. But oftentimes we can't. And that's what Agile helps us do. Once we see it, then we can react to it. There's other stuff in this universe that we can't see because it might be behind something. So if this were a galaxy, there might be stuff behind that we can't see. So that's what makes this challenging to test if we were to test a universe. So the way to deal with this is to look at it as a group of equivalence classes. So instead of looking at the universe like it's a bunch of stars, start looking at it like it's a bunch of galaxies. And in the testing world, these are really equivalence classes. So, for example, if we were testing butterflies, it's kind of concocted, but let's say we were testing the color of butterflies. That would be this equivalence class. These are all the things that we want to test for color. These might be all the things that we test for flight patterns. So that way we may have billions and billions of stars in front of us, but we're able to distill it down to what's essential to test. And so then it becomes manageable to test. You're not testing a billion things. You're testing more at a galaxy level. So now we'll start getting into actual software development and testing and the example that I'll give. But in our example, what happened was there was tons of tech debt, and we were entrusted with refactoring it so that it was truly scalable. But it had grown into something that was not scalable. And so I'll get into the details later, but if you're looking at code, you'll see these problems where people are cutting and pasting test codes, different test cases from other ones. And all of a sudden, you might have 50 to 100 pieces that are cut and paste. And to maintain that, it can be a nightmare because instead of changing something in one place, you have to change it in 50 places. So if you start doing this, you realize that you might be going down a road that it's going to be painful later. Another thing is hard coding. So when you see like file names and various package names, things that are don't necessarily belong in the code that they could, you realize that that's not going to be maintainable, and that'll be clear once I give you my example. And then if there's other indications that people are ignoring scaling by not following good code reuse practices. The reason these things are bad is because, again, you get this combinatorial maintenance explosion. Like I said, instead of changing it in one place, you've got to change it in 50 places. And that's, as the system grows, that is not sustainable. And then you start seeing test execution clogging up the pipeline. So CI pipeline. So this test may not complete. It may take too long to run. It may give you a lot of false fails. And then you're spending all your time figuring out, wait, why did it fail? When it really wasn't failure in the product. It was a problem with the tests themselves. Creating tests that scale well. This is good. So this is kind of the opposite of what I just showed you. Using good code reuse strategies. So good ones are the use of metadata, which we'll talk about in a minute, but other great ones are the use of templates and generics. So if you're familiar with, let's see, C++, they have this notion of a template. So like, for instance, a list of cars, a list of widgets, a list of pieces, whatever. That's just one piece of code. It's not cloned. You have your list of cars, list of pieces. No, it's one piece of code that you instantiate. And that's what with metadata, it's very easy to do that. And then in, I think in Java and C#, those things are called generics. And of course, there's other ways of code reuse and leveraging metadata, libraries, etc. Designing for scalability. So this is just good software design. I think in QA that can be lost because QA is often pressured. They don't have the time necessarily to deal with, or they may not be skilled enough to be really to code for scalability or to do really sound software development practices. And then another really important thing is to be aware of how long your tests take and how to deal with that. So parallelism, for example, is a classic way of being able to get your test to run faster, running 4 or 5 in parallel. And metadata, again, you can be leveraged to gain parallelism in grouping tests and being able to identify tests that are appropriate to run versus ones that are not. And again, metadata can help with that. Metadata, okay, so what is meta, besides the name of a company? Some of you may know this, but I just want to get on the same page so that we're meta joke. A meta joke would be a joke about a joke. I asked ChatGPT to give me a meta joke, and it was pretty lame. But so I won't run that by you. But suffice it to say, a meta joke is a joke about a joke. A meta word. What might a meta word be? A word about a word. So maybe alliteration would be one of them. Some grammatical term. Automatopoeia. Metacognition. What would metacognition be?
Thinking about things.
There we go. So one of my friends mentioned to me about metacognition, and I'm going, really? And apparently there was some famous philosopher, I think maybe in the 1800s, that was talking about metacognition, and it feels like pretty spiritual stuff. Metaclass. So metaclass is a class of classes. So this can probably exist in a lot of different domains, but the one I know is in small talk, they're able to modify how the language behaves in object-oriented language by making a metaclass. So for example, it's getting kind of techie, but I'll say, for an example of a metaclass would be a class where, let's say you have a two-stage constructor. For example, you can change the way a language works in object-oriented one using a metaclass. Metadata, okay, so that's what we're going to talk about today. Probably the best example would be, so this is data that would describe data. It would be in a database schema that uses tables and relationships themselves to describe tables and relationships. So that's the best definition. But usually when people talk about metadata, they just mean data that describes something. And in this case, it's in the case that I'll give, it's data that describes a data processing system. Metadata, a team hub. So before diving into the details of my example, where I was working at a large bank, regional bank in the Pacific Northwest, I can't say more. They didn't give me permission to do that. We were using metadata after our refactor as kind of a hub. So development was using it to basically write better code, so more reusable code. And I'll give an example of that. Operations was using it to actually run the system. Quality assurance was using it to test the system. Business analysts were using it to write stories. And in some cases, stakeholders or customer surrogates were getting involved. And we were using metadata as kind of a lingua franca, like the standard language across what we talk about the system across the entire team. And so it's a unifying force. Okay, so now let's get into the details here. So again, we're a regional bank here in the Pacific Northwest. This is a system that delivers business intelligence to bank executives. And so the system brings in data from hundreds of data sources. It processes it. It refines it. It finally ends up in a data warehouse where tools like Tableau, Power BI, maybe TIBCO's Spotfire, deliver nice, pretty pictures and meaningful ones that executives can understand. So that's one end user. How many end users are there? There's probably about 50 inside the bank. So this app was not used outside the bank. It was just inside the bank. And I'm guessing maybe 50 executives within the bank. Not just executives, but people that were making decisions. It was handling maybe $37 billion in loans, 45 billion in deposits. So it was fairly sizable. So a little bit more about the system. So here's our metadata. This is in a relational database. And this is an entity relationship diagram here. I put this one in orange because it's important, because this is what we're testing. So we're using SQL Server, SSIS, SQL Server Integration System, I think it's called. And this SSIS, what it does is it allows you to bring data into the system or also push it out. And that's essentially what we were testing. So usually each package would have one or more files or data sources to process. And so this metadata here, incoming data, would describe that data. And this would describe some of the packages, like the name, where it lives, what order it should be run in. As for data, let's see, name, source, location, where it might live on a file share, how often it's run or dropped, expected size range, package results. This is a metadata about the system. Over on the other side, we have test metadata, which is separate. We obviously don't want to deploy this on a production system. It's not appropriate, but it's nice when it lives on the same system. So on test systems, you can drop test metadata side by side. And the important thing is to note is that it's related to the system metadata. So relations are going this way, they're not going that way. Test results, test cases, test categories, test validations, all this kind of stuff. Test validations should map one way through here to get to the package. So I'm going to show you some pseudocode that demonstrates this, how it's accessed and used. Now, 205. 205. Oh, good. We're doing good. Generic metadata. So this is a really good way to start with metadata. In fact, this is what we did. We used generic metadata. We didn't use all that. If I could go back a slide. I put this up here just so that it's more understandable. But it can also be expressed very generically like this. So for instance, if I were to relate a test validation to a package, I could do it here. So maybe package name, validation, and then the validation script name, for example. So you can get a long ways with generic metadata. And it's a great place to start, particularly when you don't know kind of where you're going with your metadata. The system's in a greenfield state. So good place to start with metadata. Metadata coding test automation. So this is kind of it in a nutshell. You read metadata into your test automation program. For us, it was MS Test in C#. You can use an ORM, object-oriented relational management tool, where it's taking a table and mapping it into classes and objects, and you can program it in an object-oriented context. That's just one way of doing it. Metadata tables map nicely into just what it said, into object-oriented classes. Metadata tables map nicely into generics and templates. So we talked about generics and templates. These are all ways of just following good sound software engineering, where you're trying to use the least amount of code to do the most. Oh, see, sorry, guys. So this is probably the most important slide, because this is an example of, this is pseudocode. It's not really C#, but it's meant to be readable. But this is the one piece of code that, when once instantiated, replaced maybe hundreds of test cases that had been copy and pasted. So basically, we made it generic. We made our code generic. We distilled it into what was important, and everything that was individual was in the metadata. So it would read from the metadata to get all of these really package-specific pieces of information. So the frequency was in the metadata, daily. So just starting again at the top, this is a test that runs packages, just all the daily packages, happy path. So we're just doing nothing special here, just running it, assuming everything is hunky-dory. Order the packages. So remember, there was an ordinal value there. So it's going to order them. It's going to run them in a certain order. For each package in this order, list of packages, get the incoming data, which is also in the metadata, drop it, run the package, check for run status in the package results, run any validation scripts associated with the package. Again, that's in the metadata, the association there, and then log pass or fail status. So that was our basic test case for 100 packages. But so instead of writing it 100 times over, we wrote it just once. So huge win, huge win. So we reduced code by a few orders of magnitude doing that. Now, this is kind of resting over the fact that some of these things are using library functions. But that, again, is shared code. But this is it in kind of from the 50,000-foot view. That's the code that every package goes through that's daily. Now, for instance, let's say you wanted to run some failure test cases. Let's say you had a file that was corrupt and you want to run it through the package. You could do the same, something very similar, but instead of dropping this input file name into a directory, you'd have another one that was a corrupt file, for instance. And that would be test run package failure, bad corrupt file test. So that's kind of our big win there, was that we were able to reduce our code substantially. So closing up here. So some of my observations were that we were able to reduce our code at least by 10 times, sometimes more. Our false fails that were forcing us to kind of look at failures unnecessarily because the tests were broken went way, way down. Because instead of the breaking in one place, the break would be in that one piece of code. It wouldn't be distributed across 100 different files or test cases. The tests ran faster because we were able to use the metadata to write some tests in parallel versus ones that weren't. So for instance, a good metadata property would be, can these 3 or 4 tests in a group be run in parallel? So that to me is metadata. So otherwise you put that in the test, it's hard to see, but if it's in metadata, it's right there, right? Associations from test results to SUT functionality. So this is important to me because a lot of times I would look at test results from MS test and I couldn't make sense of them. And I couldn't, because I couldn't see how they were related to the actual testing and functionality. But with the metadata, it's very easy to see that because test results map to different functions directly in the metadata. So you can query what your test coverage is. If you look at, otherwise, if you're looking at MS test results, I have very little confidence in that because that mapping is not credible to me. So this makes test results to me a lot more credible. And it will also tell you, what are we testing? What are we not testing? Maybe there's stuff that we just don't want to test. For example, let's say the developer is only touching this piece of code. Therefore, he doesn't need to test everything. He just needs to test X, Y, and Z. And that's also data that could be metadata that could be put into the metadata. So for example, imagine, and maybe this could be computed, you could have, if you touch this file, you're going to want to test this function. So you can make associations between them. We haven't done that, but it's possible to do that so that you could come up with, you could compute test sets based on the code that's changed. And then finally, as I mentioned before, we had much better team collaboration. So there was no confusion about what certain terms meant. The terms were all in the metadata. Our vocabulary was metadata driven. So regardless of what team you were on, business analysts, maybe in some cases, customers, developers, QA, we all were speaking the same language. Finished. Thank you.